And yeah, thank you for the nice introduction, Carlos. And I'm going to be talking about these bow ties that we just published. And this is a part of my postdoctoral work here at the University of Michigan, Ann Arbor. And but first, before we get into like what bow ties are, I want to tell you a little bit about like how nature is using polarized light. And this has a connection with what we are trying to do with bow ties. And you will hear a bit more about it during the course of this talk here. So nature has many of you would be aware of this interesting creature called mantis shrimp. So here on the left, I'm showing you a very beautiful colored image in regular light, and you can see it has nice colors in different parts of the body of the mantis shrimp. But the mantis shrimp has a very interesting property. What is happening is on some parts of its body are actually converting a unpolarized light into a circularly polarized light. And the reason why they are doing this is because they are communicating with each other through these circularly polarized light signals, and they have their eyes which can detect this circularly polarized light as well. So what happens is when they have these burrows in the seabed or the waterbed, you will see that they do not enter anybody else's burrow because they can sense that there is circularly polarized light coming in from there. And that is how they are detecting friend or foe in that murky environment underwater. Now, how they are able to do it is also very interesting. So if you look at their body parts, which is the tail and the fins that they have, you can see that the reflected left circularly polarized light actually illuminates only those certain body parts. And these are the body parts which are used for attacking actually. And why it's rotating the light is because if you look at the cross section of these fins or the in a scanning electron microscope, you will see that there is this interesting structure where there are these building units which are rotated with respect to each other. So this is a very interesting example that exists in nature where circularly polarized light is being used for signaling in some manner between these creatures. And what this is telling us is that if you can change the structure of an object, you can actually cause it to rotate the polarization of light. And nature is showing us how it can do it. We want to take it a step ahead and tell you that if we can tune the twist in a material, then we can tune its polarization rotation. But tuning the chirality is actually not very easy. And the reason why that happens is because there are only a few stable states of a molecule which we can isolate. For example, you always see these left-handed molecules versus right-handed molecules because they are the most stable states and they can be isolated easily. However, what about if the molecules had twists which were in between the left and right? Why aren't we able to do it? Because there are these thermodynamical restrictions that are placed on these molecules. However, with large scale assemblies where instead of molecules, we start to have nanoparticles as our building blocks, we have much more control over the shape of the object and over its twist. And that's what I'm going to tell you. How am I tuning that twist by controlling the interactions between nanoparticles? And for that, I'm going to introduce to you bow ties. This is a very simple system that I found where if you look at the video, you'll see that I'm just adding one solution into other solution and it immediately turns turbid. So what is happening is that the clear solution at the bottom is that of L-cystine. That's the chiral dipeptide of cystine. And when I add cadmium into it, immediately you see that the solution turns milky and you get these beautiful structures that I'm showing here on the right hand side. This is a false colored SEM image. Now, there is a lot that is happening within this time frame that is of 0 to 90 seconds where I see this kind of turbidity appear and the bow ties form immediately. But that is the uniqueness of this system also, because we can synthesize this in water and we can do it within 90 seconds. So it's really quick, really scalable. And the bow ties that form are pretty monodispersed. The polydispersity is about like 10 to 15%. It does increase as you scale up in size, but it's still much better than other systems that are out there. Secondly, we see this very nice control over the chirality that I will show you a little bit later, where if you look at the molecule that is being used to make this structure, in this case, this is a right-handed L-cystine. And when it forms the final structure at the macro scale, which is about 2 microns or about 10 microns in size, you see this right-handed twist again emerge in the final structure as well. So there is this one-to-one transfer of chirality that is happening from the angstrom scale all the way up to the micrometer scale. And as I said, this can be scaled up really easily, and we are able to convert these into powders and then use them for different kinds of applications. However, before we start to get into like what are the applications of the system, as a material scientist, I'm always looking at these materials in this framework of this material tetrahedron. And I don't know if there are material scientists in the audience and they would appreciate this materials tetrahedron, where you study a material by understanding its structure, what is its property, and can we process it in a way where we can tune its performance. Within this framework, I'm going to take you through the talk. I'm going to tell you about what is the structure of these bow ties. Even though they form so quickly, what is actually happening within that 90 seconds. So let's go and look at it a little bit more in detail now. So the bow ties that I showed you till now, the SEM images, they were like the ones that you see on the left-hand side. It's a fully formed bow tie, is about 5 microns in length. We call this as the level 3 in hierarchy of these bow ties. It's level 3 because if you look at it a little bit more in detail, you will see that there are these small petals that are kind of arranged in a very nice, interesting manner to form that twist. How about we isolate those petals and look at them a little bit more? So if I did that, I saw that in the SEM, the petals themselves have a slight twist in them. And now this is what forms the level 2 of the system. If we go a little bit deeper into the level 2, you will see that in the petal itself, there are these small domains that are visible. That is shown here. I'm not sure if you're able to see my cursor, but that's the third from the left image. And then if you start to, but this is where the SEM stops. That's the resolution limit of the SEM, where you can see up to only a few nanometers. Then we went ahead and looked at those individual domains within the TEM. And we found that they have these very thin layers, which are about 1.2 nanometers thick, and they are stacked on top of each other. And they are really thin because if you look at the SEM or TEM image here, you will see in contrast to the carbon background, the sheets are barely visible. But they are there and they are really thin. And that is what this whole analysis tells us, that there are these 3 levels that are present in the system formed out of these thin sheets. However, there is something else that is going on. I have still not told you like what is the actual atomic structure of this material. Those thin sheets that I told you, which are 1.2 nanometer thick, what are they formed of? So to understand that we set out on a pretty long journey, and it took us like about 1.5 years, where we were trying to understand what is the atomic structure of this material. And our first clue came when we looked at the cryodiffraction pattern of this thin sheets, we saw this kind of a textured polycrystalline pattern, which says that there is some sort of ordering that is present in these nanosheets. Now, what is this ordering and what are those constituent building blocks that are making this kind of a textured diffraction pattern? So even though cryo-electron diffraction pattern gave us this detail, we wanted to extract the atomic structure. And for that, we went to synchrotron XRD. And what I'm showing you here on the right-hand side, the orange curve is what you get from the synchrotron XRD, and the blue curve is a radially averaged cryodiffraction pattern that is shown here on the left. And you can see that there is a very nice one-to-one correlation between the peaks that are present in cryo ED and synchrotron XRD, which says that when we were looking at this material in cryo ED, we were looking at its pristine state, because we all know that materials get damaged really quickly within the electron microscope. And there is an interesting story. I've written it here. If anybody wants to talk more about it, I will definitely talk in the Q&A about it. But now we are going on to the synchrotron XRD and looking at what is the structure of this material. And we sent the sample to Argonne National Lab, which is close by to my location here. And Dr. Wenqian Xu was very kind enough to put this material under the beamline and get this nice X-ray pattern for us. And when I tried to solve this structure, I found that it has this commonly seen crystal system, which is space group of P212121. And it has this lattice parameter, which is kind of similar to the L-Cystine crystal structure, but there are some intricacies there. And after a lot of like refinement and crystal structure solution and understanding different inputs from different techniques as to what bonds could be broken, what bonds could be formed, we came to this final structure that had a very good agreement with what we observed experimentally. So let me go a little bit detail about what is the atomic structure of this material. So as I said, you saw the movie where I added this liquid of cadmium into the cystine clear liquid and immediately this turbid solution forms. That's actually the molecule in one of those solutions is that cystine here, which has the sulfur-sulfur double bond, and it's about 6.5 angstrom in length. And when you add cadmium ions to it, you form immediately this kind of a 5 coordinated system where cadmium is at the center of this cluster, and there are 4 cystine molecules which are arranged in a very interesting tetrahedral pattern around this cadmium atom. And the extended structure looks somewhat like this, where I'm showing you just a projection down the C-axis. And if you look along the B, there are these stacks of, there are these layers of cadmium oxide that are present in this system, which are connected to each other by this sulfur-sulfur dipeptide linkages. And this was very interesting for us because we always thought that the system that we were forming was cadmium sulfide, but actually after solving the structure, we found that it's actually cadmium oxide and not cadmium sulfide. So till now, I've just told you that there are these 4 different levels of hierarchy, which we are able to achieve within 90 seconds in this system. And we have characterized these 4 levels of hierarchy using different techniques. For example, at the angstrom level, we did imaging and spectroscopy and synchrotronic SRD at the nanometer level to find what is the atomic structure of this material. And then we were also able to reconstruct the entire shape of this material using tomography, which I've shown here on the right. Now that we understand that this structure has all these levels, what are the optical signatures that are present in this material for all these length scales that I've shown you till now? Let's now start to look at that. So that comes to the part where what is the optical properties of this material? And that's where we will travel along this material's tetrahedron from the structure to the property of the material. So I don't think I need to talk about this, but just for the sake of introduction, I will just tell you this, that the electric field in a right-handed circularly polarized light looks something like this that I've shown here on the top left, where it's moving in a helical manner, in a right-handed manner as it propagates along its propagation direction. And the left-handed circularly polarized light looks something like this, where the electric field is moving in this kind of a helical pattern. Now, what happens is when you look at this incident circularly polarized light and it interacts with the material changes this polarization of the light and makes it some kind of an elliptical polarized light that comes out. And that is what is the rotational strength of this material, where the induced dipole moments that are arising when the light hits this material and how those induced dipole moments are placed with respect to the induced magnetic moment determines whether your rotational strength is positive or it's negative. And when you see a CD signal, you see a positive or negative bands, which pretty much corresponds to that dot product of P dot M, where if the angle is less than 90 degree, you have a positive sign. If it's more than 90 degree, you have a negative CD band. And you will see a lot of like CD spectrums in the rest of the talk. So I just wanted to give you a little bit of heads up of what we are going to be talking about now. So to understand the chiroptical response of the material, let's look at the bowties and let's look at how their chirality is affecting the CD signal. This is a very standard test that anybody who makes chiral materials does. So what I'm showing here on the top left is that when we start with the L-cystine molecule, we get these right-handed bowties. The SEM image looks something like this. And the blue CD spectra corresponds to this right-handed bowties. Now, when I flip the handedness of the molecule that I use to make this material, that is, I use the D-cystine molecule, I get these left-handed bowties that are forming where the handedness completely flips. And the spectra, the CD spectra, as usual, splits as flips as well, where you see the red spectra is actually a mirror image of the blue spectra. Now, what is interesting is that when you have an equal mix of L molecule and the D molecule, that's a racemic mixture, you get these flat stacks of like sheets which look like pancakes, and they are chiroptically silent. You don't see any signal when you look at this material and put them under the circular dichroism spectrometer. So that is the flat black line that's coming from these racemic bow ties. And this is a typical absorbance or extinction spectra that I'm showing here that corresponds to these kind of structures. Now, this is the time actually what happened was the pandemic hit around 2020. And I had all this experimental data, and I wanted to understand like how this chiroptical spectra that I'm getting is appearing. What are these bands corresponding to, and why we see this kind of a signal when this kind of a twisted structure is present. So what I did was during that time, I got deeper into the simulation side of the chiroptical spectra, and I took the SEM images, measured them in MATLAB, all their dimensions, and created a very simple model where using the experimental parameters, where I created a stack of twisted sheets of this kind of a length. And then I started simulating their chiroptical spectra using this method of FTDT in Lumerical, which is a commercially available software. And so when you think of these bow ties, they are actually present in solution. There are many of them, and they are all rotating all around when you are measuring the circular dichroism spectra. To mimic that situation in the simulations, I took this model and I rotated it all around in three-dimensional space and calculated the chiroptical spectra for each of these orientations. And that's what is shown here in this G factor spectra that you see here. So you will see that the bands are kind of modulating as the angles are changing. And then I average all of them, and then I plot my G factor spectra, and you can immediately see that there are these nice bands that were already we saw in the experimental spectra that are actually emerging here as well. And the same idea that when you flip the handedness of the model, you actually get a flipped spectra as well. But the simulation actually goes further and tells you a bit more about like how these bands are arising, whether they are arising due to absorbance or scattering. And what we saw was that all these bands that you see above 500 nanometer in wavelength, they are a direct result of the scattering phenomena, where the differential scattering is dominating this kind of a spectra that you see here. And the simulation again goes ahead and tells us that we can actually look at how the left circularly polarized light is individually giving us this kind of a spectra, and how the right circularly polarized light is giving this extinction cross section. And the difference of these two is what is plotted in the plot right above it. And that's the CD or G factor spectra that you see. So, okay, we understand that, okay, scattering is the dominant phenomena here when we look at these bow ties. Now we can take the simulations a little bit more further and start to look at how the scattered field around this kind of a twisted bow tie looks like. Okay, so what I'm showing here is the model that I just showed you, but now this is the model which has now interacted with the light, and the scattered field is plotted around it. So the blue curves or the blue regions that you see is basically the scattered field that is present around this model when the left circularly polarized light is hitting the structure. And the model itself is right-handed in nature. Now what happens when right-handed circular polarized light hits this right-handed bow tie? You immediately, when you look at these two pictures or these two columns, you will see that there is this intense red region that is present in this system when the handedness of the light matches the handedness of the bow tie. And what is happening is the electromagnetic field is being concentrated between the gaps that are present in this stacked layers that I've created synthetically and also modeled. And that's a very interesting phenomena, because this can actually be leveraged in different kinds of situations. For example, a lot of people try to like absorb molecules on surfaces and then use light to excite or drive reactions. If you can confine light and absorb them in a controlled manner in this kind of a system, you can actually take this system much further and do a lot of different chemical reactions which are catalytically driven and which are also enantiomerically enriched or enantioselective in nature. And so this, I just told you a little bit about what we can do in the future with this kind of materials, but to bring it back to what we are doing here, if you take the difference of the left circularly versus the right circularly polarized light, you immediately see that the difference is coming because of the stacking of the sheets and the electromagnetic field being concentrated in the between the sheets. So now what I've told you till now is that we looked at the UV vis to near IR region of the spectra or the chiroptical fingerprint. But if you remember, I told you that the chirality is actually present in the clusters or the atomic structure that I showed you at the angstrom level, and it's also present at the nanometer or the micrometer level. So when you look at the CD spectra, that is in the micron size, that's where you were seeing an effect of the entire micron size structure. But what is happening at the atomic level here? Okay, let's start to look at that. So for that, we had this very coincidentally, we bought this VCD instrument from JASCO around like 2020, 21. And we started to look at this material under the VCD spectrometer. And what I found was that when I put this material in the VCD and look at the amide 1 and 2 band, I see very intense bands of the VCD spectra, which are of the order of like 0.01. So what I'm pointing out is this y-axis here on the top left curve, where the VCD spectra is pretty intense. It's 0.01. So when I say pretty intense, the reference point that I have is if I just had a cystine molecule which was not bonded to the cadmium like in bow ties, you will see this spectra which is very weak, and it would be of the order of 0.0001. That's about 10 raised to the power -3 to 10 raised to the power -4. But what happens is when it bonds to cadmium, there is this intensification of the spectra or the intensification of the rotational strength at that molecular level. Now, why is that happening? And that was a question that was burning in our minds for quite some time. And luckily at a conference, we met Paul Nicu, who's in Romania, and this conference was the CD 2022 conference. And he was very interested in this idea of why this intensification of VCDs or the enhancement of VCD spectra happens when you have these kind of metal organic kind of linkers present in the system. So what we found was that because this cadmium is bonded to the oxygen of the cystine molecule, there is this kind of a charge transfer that is happening. And then since these cadmium is bonded to 4 different, there is also this coupled oscillations that are happening together. So this coupled oscillations are actually giving rise to this kind of an enhancement due to the ordering within this cluster that we have at the nanoscale. And he was able to isolate like what these bands correspond to, where if you look at the most intense bands, it's actually a COO stretching band, but it is also contaminated with the HNH scissor oscillations that are present. And that's what the movie here is showing you. And we can go more into the details of this, but I'm going to like limit it to this point, but we can talk a bit more about it during the Q&A as well. So now we have seen that, okay, at the molecular level, there are these individual bonds that are vibrating and that are presenting themselves in the VCD spectra, and we can interpret them based on the structure as well as on the spectra. Now that is present at, if you look at the scale bar or the x-axis here, the wave number is from 1500 to 1700. And these are about 0.198 EV kind of vibrations that are present. But since this structure has certain level of order at the nanoscale, if you remember the diffraction pattern that has that texture indicates that like there is some kind of ordering that is present. So what that means is that there should be some kind of collective vibrations also present in the system. And since chirality is present at all levels, those vibrations should be chiral in nature. So for that, we have a very nice system in our lab in Kotov lab where Dr. Wonjin Choi developed that system of measuring the terahertz circular dichroism of the material. And when we put this material under the terahertz circular dichroism spectrometer, we saw these very weak vibrations of about 7.5 milli EV, and they are actually mirror images of each other, which indicates that these collective vibrations are actually chiral in nature. So, and what do those collective vibrations look like? So with simulations, we saw that the cadmium atoms act like a hinge, and these molecules which are chiral, they actually rotate about that hinge in a collective way in a handedness, with a handedness to their vibrations. And one of those collective vibrations is what I'm showing you here. So to summarize all the chiroptical spectra till now I've shown you, what we are doing is we are actually able to see what is the circular dichroism spectra that appears in the UV vis to IR region using a regular CD instrument. Then if we look at the amide region and the far IR vibrations, we can actually look at the local molecular vibrations using the VCD spectrometer, that is the middle plot, and how those local vibrations couple with each other and vibrate or like collectively rotate. That are the chiral phonons that we can map using the terahertz spectroscopy that's shown on the right. And if we start to now correlate the spectra that I've shown you till now with the spatial distribution or the spatial nature of this vibrations, we can actually start to interpret the results or the peaks that we see in these spectra. And these are the vibrations that I showed you through simulations. So we have mapped a very huge range of this wave numbers all the way from 10,000 centimeter inverse to 100 centimeter inverse using different instruments and having a very clear understanding of what the structure is like, what the experiments show us, and what we can do with simulations. So now we have a very clear, at least a good understanding for us as to what is the structure, what is the optical property of this material, and how they are correlated. Since we understand this, now we should start to tune this. So if I tune my structure like what the mantis shrimp was doing, it had this small building blocks which were rotated and it was rotating the polarization of light. Now, if I can go one step ahead and tune my structures continuously, then I can actually tune my optical property. How do we do that? And for that, we have to start understanding how this material forms. And we collaborated with Professor Sharon Glotz and Dr. Thi Wo, who are experts in modeling the self-assembly of nanoparticles. And this atomic structure that I solved, I gave it to them. They took the atomic coordinates from there and they did their whole magic. I'm not going to go into the details of it. It's written here. But ultimately, what they did was you have to focus on this right-hand side where the complexity of the molecular structure or the atomic structure that was there, they isolated what are the primary interactions that are present between these nanoclusters or the nanoparticles that are there. So they identified 3 sites, which is the hydrogen bonding that is present in the system, how the covalent bonds that are the sulfur-sulfur linkages that are there, how strong they are, and what are the charge interactions that are present in the system between the cadmium atom and the oxygen atoms that I have been using during my synthesis. And they found that the electrostatic interactions are pretty strong and they have the most effect on the final structure that forms of the bow ties. And the way they did this was they did the Monte-Carlo modeling of these building blocks, which they have coarse grained, and they have shown here. And they computed what are the potentials of mean force when these building blocks are interacting with each other along 3 perpendicular directions that are D1, D2, D3, which corresponds to the different bonding types that are present in this material. And what they found was that since the electrostatic interactions were pretty strong, and if you let this structure stabilize and grow using a Monte-Carlo model, if you start with this kind of a chiral building block at the atomic level, you start to see these kind of twisted platelets that emerge in the model. For example, one of them is shown here, which is about 100 to 200 building units, about 20 nanometer in size, and it has a slight twist in it. And you let these systems grow further and you have larger building blocks, you start to see the emergence of these very large twisted structures of the order of 200 nanometers, which was roughly our level 2 of hierarchy in the bow ties. But if you have an achiral building block at the atomic level, it actually forms a flat platelet as shown here. So I think I have 15 more minutes. If there are any questions, please feel free to ask. Otherwise, I'll just keep going. So in these, so what these simulations told us was that there is this strong effect of electrostatic interactions and van der Waals forces that are competing with each other, where the ones as the building units are attaching with each other.
Prashant.
Yep.
There is one question that we have for our team. Is asking how important is the cadmium in the formation of the bow tie structures, and could you replace it with a different transition metal like zinc or mercury?
Yes. That's a great question. And actually, you can, and we did in our paper, you will see in the supplementary buried somewhere. We have looked at different metal ions, how they are coordinating with different cystine molecules. And we saw that actually at the same conditions, only cadmium is giving us this kind of a twisted structure. But when you replace it with different metal ions, they give you different shapes, not the bow tie shape that you see. They still have chirality in them, but the bow tie shape does not emerge. And the reason is because the potentials of mean force that I just showed you, they actually change because they are dependent on what are the atomic interactions and what are the charge transfer interactions that are happening between the organic molecule and the metal ion. So yes, you can use different metal ions. You might have to tweak the conditions. For example, this is all happening at the room temperature. You might have to change the temperature of the system or change the pH of your of the chiral solution to form and get to a similar structure. So what I'm saying is you can form bow ties using different metal ions, but you might have to explore a slightly different design space to get there. Is there any other question?
That was the only question. You can continue, Present. Thank you.
Okay. So yeah. So coming back to this, so we have these building blocks which are charged and they are interacting with each other, and electrostatics is playing such a huge role, and we know that through the simulation. So now can we put that to test through our synthesis method as well? So this is very basic high school physics kind of experiment where when you have two charges, you can change the interaction between the charges if you change the dielectric medium that is present in between them. And that dielectric medium in our case is a solvent. So when you have water, you see this kind of a twisted structure form. I'm pointing to the more left, right bottom panel here. And when you start to change the solvents, you see that the interactions between the nanoparticles are changing. And so you see there is a decrease in stacking. That is, the layers are not stacking as well together. So you can control the dielectric medium, you can control the shape of the bow ties. Similarly, if you change this now, if we go to the topmost scenario where you are using sodium chloride is a very effective screening agent. So if you add like common salt, so if you start to add common salt in your solutions, you will see that the nanoparticles now don't see each other that well. So they can now come closer to each other and they can start to form very thick and fat bow ties, as you see at the rightmost panel here at 0.5 molar NaCl concentration. So we can have this very nice one-to-one correlation between what are the electrostatic interactions at the molecular level and how they are translating all the way up to the micron level. And pH, until now, I have not talked about this, but is actually the most important factor which determines whether you can form a bow tie or not. When the pH of the cystine solution determines what is the charge on the COOH group that is present in the cystine molecule, and that determines whether you get that twisted bow tie or not. So if you are off the pH, you will not see these kind of fully formed bow ties. Instead, you will see these very crumbled structures, which are very much looking like flat pancakes. And so I've talked more about most of the parameters. So, but what this allows us to do is now we have these multiple physical chemical knobs where we can use them to tune the structure. We have a very clear understanding of the structure, the optical signal that is present, and also how it forms. So now we can use these temperature, charge screening, counter ions, and solvents to change the structure and create these phase diagrams and access and open up a huge library of structures. So for example, what I'm showing here is a phase diagram where the x-axis is the cadmium ions in the solution and the y-axis is the amount of L-cystine ions in the solution. And you can see as you go along the x-axis, you will see that this, if you look at the bottommost panel, you will see that the size continuously decreases. If you go along the y-axis from the bottom, you'll see as you decrease the amount of L-cystine and you increase the amount of cadmium, you will see that the size again decreases. So you have a very good control over the size depending on how much cadmium and how much L-cystine you add in the system. You can start to take that a bit further and construct more phase diagrams where instead of having no salt in the solution, you can construct an entire phase diagram having about 0.25 molar salt in the solution, and you will immediately see that the bow ties that are forming are much thicker, much fatter in shape and size, as shown in these SEM images here. Now comes the part which is the most interesting here is the chirality continuum that is present in the system. So we have this huge control over the shape of the material, but can we control the amount of twist that is present? So this is a phase diagram where on the x-axis, I'm changing the amount of chiral molecule that is present in your starting solution. So on the left-hand side, you have all the D-cystine molecules that were used when making this bow ties. On the right-hand side, you have only L-cystine molecule that was used. So the handedness is flipped. However, when you use intermediate amounts of L versus D, you see that the twist is actually continuously decreasing. And finally, at the equal parts of L and D, you see this kind of of these flat bow ties or flat pancakes that are forming. And this continuous twist has never been seen in any other micron size assemblies which are formed from the bottom up like this. And this was a big deal for us because now if we are able to tune the twist in the material at the micron scale so continuously, we can now tune the optical signature of the material as well very continuously. So let's come to that now. So I've been showing you all these beautiful structures that can form and we can control the shape and size. But when we look at the CD spectra, they are actually continuously tuning as well, as shown in the CD curve, where we see this kind of a continuous shifting or increase or red shift of the spectra as the size of the bow ties is increasing. But now we have all these structures. How can we start to analyze these structures and get to a situation where we develop some kind of a mathematical understanding of this huge design space that is present? So what we did was we broke down this spectra into these P1, P2, P3 peaks, and we started to break down the structure into its morphological parameters, that is the length, width, thickness, and the twist angle in the material. And we started to see what would be the best way to correlate this kind of a structure, morphological parameters, and the spectral peaks that we see. And for that, we came to this chirality measures that are well known in the chirality literature, where what we did was we broke down this entire twisted model that is shown here on the right-hand side, and we looked at the center of into 8 parts. So you decide what is the center of your bow tie, and then you break it into 8 octants. And then in each octant, you look at the center of mass of that octant and start to see what is the achiral version of that 8 points that would be present in the system. And then you compare how far this kind of 8 points are from that achiral set of points using this chirality tensor that is shown here. That is the formula, and that gives you the chirality measure. So I'm just giving you a very brief overview of the system. You can read more about this in this original paper by Osipov, and these are called as OPD indices. So what OPD indices do is they distill your length, width, thickness, and pitch into single parameter. And what I've done is I've measured all these length, width, thickness, and twist angle from the SEM images, converted them into the OPD indices, and you see that there are these empirical relations. This is just for our sake that we are able to see this kind of a dependence of length, width, thickness over OPD. Now we do the same thing with the spectra that we had, the P1, P2, P3 peaks, and look at how these peaks scale with the OPD indices of the material. And this was very interesting because what we saw this kind of an exponential relationship between the OPD indices and the peaks. Now what this allows us to do is we can now correlate both the spectra, that is the curve on the left, the peaks, with the OPD indices, and we can also correlate the structure with the OPD indices. So now you can come and tell me, I want a material which gives me a specific polarization rotation at this lambda. I will go back and look at my design space and this chart and say that, okay, this is the OPD index I would need, let's say about 4.4 or 4.5. I'll go back and look at the structural OPD index calibration chart and look at what would be the length, width, thickness, and pitch I would require and go and make that structure. And that is exactly what we did. We wanted a material which would give us a peak highest G factor peak at 1550 nanometer. I went and did that and created this bow ties using a 50-50 mixture of acetonitrile and water. This is what the bow ties look like. This is what the CD peaks look like. And what I did was I coated them on different materials. For example, I mixed them in a polyacrylic acid, coated them on glass, coated them on cloth using both L and D bow ties, and that's what is shown here. And now we start to compare what these coatings can do as compared to what mantis shrimp could do. So now these coatings have these twisted structures within them, like the mantis shrimp had these twisted rods inside its shell. And now we start to put these coatings to test. And that's where the performance of this material comes. How do we evaluate the performance of these coatings? And for that, Minjong Cha in our lab developed this LIDAR system where we had this a 1550 nanometer laser, which was circularly polarized light, and our coatings were placed somewhere here. And then we look at the reflected signal when the circularly polarized light hits this sample. This is what the setup actually looks like, and the object is placed here. A lot of optical elements that are present in this. But when we look at the actual signal that comes out, if you look at the L bow tie that I created, the coating here, you will see that the reflected signal only shows this kind of a blue dots. The blue dots here correspond to minus 0.05, which is about a 5% polarization rotation efficiency. And the way we are measuring it using a same formula as the G factor, where the incident left circularly polarized light and the incident right circularly polarized light signals are measured from the coating, and they are subtracted with each other and normalized with respect to the sum of those two signals. And that's what is shown. So you see when left circularly polarized light hits the L bow tie, so there is a handedness mismatch. L bow tie are right-handed, and the left circularly polarized light is basically left-handed. So you see that the signal is negative. But when the right circularly polarized light hits the right-handed bow ties, you see that the signal is more intense, and you see this kind of a positive signal in the maps that we have. So when you coat this on cloth, actually, you can see that the cloth itself has this kind of a background signal, which is actually coming because of the twisted fibers that form this cloth. So D bow ties, when the handedness of the D bow ties matches the handedness of the cloth in the background, even though you can see them with eye, but when you look at them using the laser, the circularly polarized laser, they are pretty much invisible. So what we are trying to demonstrate here is that you can start to use these materials as fiducial markers, where these LIDAR ranging systems can now start to detect these markers even in night and even from like small, simple white dots itself, even though you cannot differentiate between those white dots, but they would have very complex spectral signature embedded within those white dots, and they can be used as unique markers. So in summary, I have shown you that we have created this material system and evaluated it using this materials tetrahedron by understanding what is its structure, property, and how we can process it and tune it to actually change its performance. And we have created this tunable bow tie metamaterial. We can tune its structure across a huge range of sizes, all the way from 500 nanometer to 4 micrometer, while maintaining the twist intact. We have developed quantitative structure property correlations between this material. And I hope we are doing, without offending the mantis shrimp, we have done slightly better in tuning our material as compared to mantis shrimp, where it has a fixed structure in its shell. And you can read more about this in our paper here. And I would like to acknowledge a lot of members of Kotov Lab who were involved in this study and who helped throughout this study for about like 4 years on this system. Glotzer group members, especially Theo, who helped with the modeling, and my undergrad students, Alex Simon and Daniel Katz, who are now grad students in UCLA and Northwestern. And they helped me create these huge libraries of bow ties, which I showed you in some of the phase diagrams. And I'll be happy to answer any questions, and please feel free to ask. Thank you. Hi, Carlos. Are there any questions?
I have a question, and I think it's related. I thought that you did a lot of. We're looking at different concentration at the cystine and also different solvents. And you were talking about the chirality at different levels, like nanometer level, micrometer level. But at the beginning, you were talking about, I think, a starting powder. So I'm just
Yes.
curious if this starting powder was at nanometer level, or what was the starting powder size? If
Oh,
and if that it matters.
okay. Let me see if I understand your question. So you are saying that in the beginning, when I make this material, the powder that I use, what is that? Whether it's nanomaterial level or
Uh-huh.
what is that, right?
Yes.
Is that okay? Okay. So let me open up that slide. So you're talking about this, right? So when I'm actually here. So these are commercially available cadmium chloride salts that I bought from Sigma Aldrich, and L-cystine is also commercially available from Sigma Aldrich. These are powders. You dissolve them in water. You get these clear solutions. L-cystine does not form this clear solution. You have to change its pH by using NaOH so that it's able to dissolve. And that's basically what the starting solution is. It starts from these commercially available powders. You mix them in water, you mix them together, and you form the structure. Now you can take this solution and freeze dry it and convert it into a powder, which I've shown here. And the powder itself actually contains all these bow ties inside them. So does that make sense?
Yes.
Okay.
Again, if somebody wants to make a question, you can go to the Q&A. You can write your question there, and some of our members are going to read it. Let's wait a couple of minutes, Prashant. So if somebody have a question, I'll let you know.
Okay.
So, Prashant, I think with that we are going to finish because the time that we set out for today is like 1 hour. We are reaching the point.
Thanks,
And
Gregory.
I don't see any questions. I just see comments that this is a great presentation, very nicely done. Again,
Thank you.
thank you, uh, Prashant. Thank you all the attendees, and I hope that we can set up soon a new webinar with an exciting topic. Okay, thank you everyone, and have a good day.
Bye.